Alright, so in this video we're going to use the equations we came up with in the last video and look at a simple example here. So we're looking at a carbon epoxy layer. In case A, that layer is aligned such that the fibers are all in the X direction, and in the example B, they're oriented at 30 degrees relative to the x-axis. Now, in this case, we're going to assume that there's a strain, 1%, that is a strain of 0.01, in the x direction, with the other strains being constrained to be equal to 0. Okay, so we're going to try to find the stresses associated with this. Here are the properties of carbon epoxy. And again, what we're trying to find are the stresses in both the local and the global coordinate system for each one of those two layers. So we'll start out by looking at the reduced stiffness matrix, that is the Q matrix. And here's our equation that we came up with last time for the terms of the Q matrix. Notice that again, it is symmetric, so I've just used the nu 1, 2 times E2 for both of these. Now you notice here we were given these four constants here, but we have to have nu 2, 1 as well. So if you recall, nu 2, 1 is related to nu 1, 2 by the ratio of the moduli. That should be, E2 divided by E1 right here. So 1.2 million divided by 20 million times 0.25. So nu 2, 1 tends to be very, very small. And this quantity 1 minus nu 1, 2 times nu 2, 1, you can see that's very, very close to 1. So when we divide these values by that quantity, they're not going to change very much. So this 20 million becomes 20.08 million. The 1.2 million, 1.205. Again, all of these multiplied by 1 million. And you can see here once we multiply by the Poisson's ratio right here, and G12 is just as is, 0.8 times 10 to the 6th psi. All right, now again, that's the same for both because this is in the local coordinate system. But now when we want to do the Q bar matrix, that is the reduced stiffness matrix in the global coordinates, then we have to transform those. Now, of course, for the 0 degrees, the cosine of 0 is 1 and the sine is equal to 0. And there's the cosine and the sine of a 30-degree lamina. And so we plug into our equations that we came up with last time, those lengthy equations for the Q bar matrix that you'll end up putting in a spreadsheet pretty soon. And of course, the Q bar matrix for the 0 degree is exactly the same as the Q matrix. Whereas for the Q bar matrix, you can see the terms that are there. And again, all of these are in million psi. Notice for the Q bar matrix that the Q bar 1,6 and Q bar 2,6 are both non-zero, whereas for the 0 degree laminate, those are 0. And again, what that means is that for this 30 degree laminate, if you pull it in the x direction, it's going to have some in-plane shear. All right, now to find the stresses, let's take the Q bar matrix and multiply by the global stresses, which are again, epsilon x being 0.01, epsilon y is 0, gamma xy is 0. And so there's what you get for the 0 degree laminate, which kind of makes sense. You're going to generate a high stress in the direction that you're straining it. Now the 3000 psi tensile strength in the two direction makes sense because you're constraining it. Once we set the normal strain in the y direction to be equal to 0, normally that would want to shrink a little bit in that direction. So when you set that to 0, you're actually saying we need to have a stress to be associated with that. So it's being pulled in tension to be able to hold the strain equal to 0. Hard to make those same comparisons in the 30 degree laminate, so you end up with high values of sigma y and shear stress tau xy. Now, to transform those into local coordinates, we look at the T1 matrix and multiply, and by the way, of course, for the T1 matrix for the 0 degree lamina is just the identity matrix. And we do that multiplication, And again, see that for the 0 degree, of course, the stresses in the global and local are exactly the same. And for the uh, uh, 30 degree laminate, you can see the global stresses are as shown on the bottom there. Now, there is a different approach you can take, and I'll just show this for the 30 degree layer. Notice last time what we did was transform the strains, multiply by the Q bar matrix, excuse me, we multiply by the Q bar matrix first, then transformed. This time what we're going to do is transform the strains at the very beginning into the local coordinate system. And again, this is for the 30 degree layers, so that 0.01 epsilon x transforms into these strains in the 1, 2 directions. And then you just have to multiply that by the Q matrix rather than the Q bar matrix. I like this approach a little better just because there's a few zeros here, so there's a few less calculations to be done, but not a big deal either way. And so we come up with these values for sigma 1, sigma 2, and tau 1, 2, which are the same as we did earlier. Now, to find the stresses in the global coordinate system, we multiply by the T1 inverse matrix. And we'll see again that the stresses that we come up with are the same as when we took the Q bar matrix and multiplied it by the global strains. And by the way, in the reading this week, something about making sure that you use the proper number of significant digits. Now I've shown here for 4 because we want to be able to compare the two approaches, but normally you want to carry intermediate results to a lot more digits and get your final answers down to 3 significant digits. So with that in mind, we now know how to look at stress and strain and the relation for a single layer. And now we can actually do something more, gets more toward the heart of this class, that is be able to put loads on a laminate and see what the stresses are in the layers. So next time we'll start on the extensional behavior of a symmetric laminate using the equations we've developed for layers and assembling them into the mechanical properties and stress strain response of the laminate.